National Electrical Code Section 240.81 addresses circuit breaker position. This section states that panel boards must be mounted in cabinets or enclosures and must be dead front. A dead front design prevents unintentional electrical contact with live parts. While 240.81 doesn't explicitly mandate the position of circuit breakers, the code intends to prevent accidental contact with live parts. Mounting circuit breakers in the up position when on reduces the risk of accidental engagement or disengagement, lowering the chances of arc flash or shock hazards. Keeping circuit breakers in the up position when on is generally recommended for safety. National Electrical Code Section 240.30 pertains to enclosures for breaker panels. It dictates that all circuit and disconnecting breakers must be enclosed or guarded to prevent accidental contact with busbars or other live parts. While covers aren't explicitly mentioned, they are a common method of providing protection. Leaving breaker panels uncovered in areas accessed by patrons and use could violate code. Requiring the electrician to change the position of the circuit breakers to the up position when on enhances safety. It is essential to install covers or enclosures to comply with 240.30 and protect individuals from potential electrical hazards. Breaker panels are enclosed to prevent accidental contact with live electrical components. These enclosures are designed to protect individuals from electrical shock and to prevent damage to the electrical system. There are several types of enclosures available, each designed for specific applications and environmental conditions. Understanding the requirements for breaker panel enclosures is crucial for ensuring electrical safety and compliance with electrical codes. Firstly, enclosures are typically constructed of metal or non-conductive materials such as plastic or fiberglass. Metal enclosures provide superior protection against physical damage and electrical interference and are often used in industrial or commercial settings. Non-conductive enclosures are suitable for environments where corrosion or chemical exposure is a concern. Secondly, enclosures are classified based on their ability to protect against environmental factors such as dust, water, and corrosion. The National Electrical Manufacturers Association (NEMA) provides a standardized system for rating enclosures, with NEMA ratings indicating the level of protection offered. For example, a NEMA 1 enclosure provides protection against contact with enclosed equipment, but does not protect against water or dust. A NEMA 3R enclosure provides protection against rain, sleet, and snow, while a NEMA 4 enclosure is watertight and can be used in wet environments. Thirdly, the selection of an appropriate enclosure depends on the specific application and the environmental conditions at the installation site. For indoor applications in dry environments, a NEMA 1 or NEMA 2 enclosure may be sufficient. For outdoor applications or in environments where exposure to water, dust, or corrosive substances is likely, a NEMA 3R, NEMA 4, or NEMA 4X enclosure is recommended. Fourthly, enclosures must be properly sized to accommodate the circuit breakers and other electrical components they contain. The enclosure should provide sufficient space for wiring and connections, and should allow for adequate ventilation to prevent overheating. Overcrowding an enclosure can lead to equipment failure and increase the risk of electrical hazards. Fifthly, enclosures must be installed in accordance with electrical codes and manufacturer's instructions. Proper installation includes securely mounting the enclosure to a wall or other support structure, ensuring that all wiring connections are properly made, and grounding the enclosure to provide a path for fault current. A proper installation can compromise the protection provided by the enclosure and increase the risk of electrical shock or fire. Sixthly, regular inspection and maintenance of breaker panel enclosures are essential for ensuring continued protection and compliance with electrical codes. Enclosures should be inspected for signs of damage, corrosion, or water ingress, and any necessary repairs or replacements should be made promptly. Additionally, enclosures should be kept clean and free of debris to prevent overheating and maintain proper ventilation. Seventhly, in addition to providing protection against environmental factors, enclosures also serve to prevent unauthorized access to electrical components. Enclosures are typically equipped with lockable doors or covers to prevent tampering and to ensure that only qualified personnel have access to the electrical system. This is particularly important in areas where the public or untrained individuals may be present. Eighthly, when selecting an enclosure, it is important to consider the specific requirements of the electrical system and the environmental conditions at the installation site. Factors such as the size and number of circuit breakers, the voltage and current ratings, and the presence of corrosive substances or explosive atmosphere should all be taken into account. Consulting with a qualified electrician or electrical engineer can help ensure that the appropriate enclosure is selected for the application. Ninthly, enclosures are available in a variety of configurations, including surface-mounted, flush-mounted, and freestanding models. Surface-mounted enclosures are typically mounted directly to a wall or other flat surface, while flush-mounted enclosures are recessed into the wall to provide a more aesthetically pleasing appearance. Freestanding enclosures are typically used for larger electrical systems and can be placed on the floor or mounted on a pedestal. Tenthly, the cost of a breaker panel enclosure can vary depending on the size, type, and NEMA rating. Metal enclosures are generally more expensive than non-conductive enclosures, and enclosures with higher NEMA ratings offer greater protection and come at a higher cost. However, the cost of an enclosure is a small price to pay for the protection and safety it provides. It is important to invest in a high-quality enclosure that meets the specific requirements of the electrical system and the environmental conditions at the installation site. The electrical code specifies requirements for the installation and maintenance of electrical equipment, including breaker panels and their enclosures. These requirements are designed to ensure the safety of individuals and property and to prevent electrical hazards. Some key electrical code requirements for breaker panel enclosures include: firstly, enclosures must be listed and labeled by a recognized testing laboratory such as Underwriters Laboratories, UL, or Intertek, et al. This ensures that the enclosure has been tested and certified to meet applicable safety standards. Secondly, enclosures must be installed in accordance with the manufacturer's instructions and the electrical code. This includes properly mounting the enclosure, making secure wiring connections, and grounding the enclosure. Thirdly, enclosures must be sized appropriately for the circuit breakers and other electrical components they contain. The enclosure should provide sufficient space for wiring and connections, and should allow for adequate ventilation to prevent overheating. Fourthly, enclosures must be protected from physical damage and environmental factors. This includes protecting the enclosure from impact, corrosion, water ingress, and other hazards. Fifthly, enclosures must be accessible for inspection and maintenance. The enclosure should be located in a place where it can be easily accessed by qualified personnel and should be kept clear of obstructions. Sixthly, enclosures must be properly grounded to provide a path for fault current. Grounding helps to prevent electrical shock and to protect equipment from damage in the event of a fault. Seventhly, enclosures must be equipped with appropriate warning labels and markings. This includes labels indicating the voltage and current ratings of the equipment, as well as warnings about potential electrical hazards. Eighthly, enclosures must be maintained in good condition. Regular inspections should be conducted to identify any signs of damage, corrosion, or water ingress, and any necessary repairs or replacements should be made promptly. Ninthly, enclosures must be kept clean and free of debris. Dust, dirt, and other debris can accumulate inside the enclosure and cause overheating or other problems. Tenthly, enclosures must be locked or otherwise secured to prevent unauthorized access. This is particularly important in areas where the public or untrained individuals may be present. Complying with these electrical code requirements is essential for ensuring the safety and reliability of electrical systems. Failure to comply with these requirements can lead to electrical hazards, equipment damage, and legal liability. Consulting with a qualified electrician or electrical engineer can help ensure that breaker panel enclosures are properly installed and maintained in accordance with applicable codes and standards. The National Electrical Code, or NEC, provides specific guidelines for the installation, maintenance, and safety of electrical systems and equipment. Several articles within the NEC directly address the requirements for circuit breakers and their enclosures, ensuring safety and compliance. Firstly, NEC Article 240 covers overcurrent protection. This article details the requirements for protecting electrical systems from overcurrents, such as short circuits and overloads. It specifies the types of overcurrent protective devices that are permitted, including circuit breakers and fuses. Article 240 also addresses the requirements for interrupting rating, which is the maximum current that a circuit breaker can safely interrupt without causing damage to itself or the electrical system. Secondly, NEC Article 312 pertains to cabinets, cutout boxes, and meter socket enclosures. This article outlines the requirements for the installation and construction of enclosures used to house electrical equipment, including circuit breakers, switches, and metering devices. It specifies the types of materials that are permitted for enclosures, as well as the requirements for dimensions, clearances, and access. Article 312 also addresses the requirements for protecting enclosures from environmental factors, such as moisture, dust, and corrosion. Thirdly, NEC Article 408 covers panelboards. This article provides requirements for the construction, installation, and protection of panelboards, which are assemblies of circuit breakers or fuses used to distribute electrical power to branch circuits. It specifies the types of panelboards that are permitted, as well as the requirements for overcurrent protection, grounding, and wiring. Article 408 also addresses the requirements for marking and labeling panelboards to identify the circuits they serve. Fourthly, NEC Article 110 addresses requirements for electrical installations. This article covers general requirements that apply to all electrical installations, including requirements for workmanship, wiring methods, grounding, and overcurrent protection. It also addresses the requirements for identifying and marking electrical equipment, as well as the requirements for providing access to electrical equipment for inspection and maintenance. Fifthly, NEC Article 230 covers service entrances. This article outlines the requirements for the service entrance, which is the point where electrical power is delivered from the utility company to the building. It specifies the types of service equipment that are permitted, as well as the requirements for overcurrent protection, grounding, and disconnecting means. Article 230 also addresses the requirements for protecting service conductors from physical damage and environmental factors. Sixthly, NEC Article 250 pertains to grounding and bonding. This article provides comprehensive requirements for grounding and bonding electrical systems and equipment to ensure safety and prevent electrical shock. It specifies the types of grounding electrodes that are permitted, as well as the requirements for grounding conductors, bonding jumpers, and equipment grounding conductors. Article 250 also addresses the requirements for grounding sensitive electronic equipment to prevent noise and interference. Seventhly, NEC Article 430 covers motors, motor circuits, and controllers. This article provides requirements for the installation and protection of electric motors, motor circuits, and motor controllers. It specifies the types of overcurrent protection that are required for motor circuits, as well as the requirements for disconnecting means, motor control centers, and motor overload protection. Article 430 also addresses the requirements for protecting motors from overvoltage and undervoltage conditions. Eighthly, NEC Article 500 through 516 cover hazardous locations. These articles provide requirements for electrical equipment and wiring in hazardous locations, such as areas where flammable gases, vapors, or dust may be present. They specify the types of equipment that are permitted in hazardous locations, as well as the requirements for explosion-proof enclosures, intrinsically safe circuits, and other safety measures. Ninthly, NEC Article 547 covers agricultural buildings. This article provides requirements for electrical equipment and wiring in agricultural buildings such as barns, poultry houses, and greenhouses. It specifies the types of equipment that are permitted in agricultural buildings, as well as the requirements for grounding, bonding, and corrosion protection. Article 547 also addresses the requirements for protecting electrical equipment from moisture, dust, and rodents. Tenthly, NEC Article 690 covers solar photovoltaic systems. This article provides requirements for the installation and operation of solar photovoltaic (PV) systems, including requirements for overcurrent protection, grounding, disconnecting means, and wiring methods. It also addresses the requirements for protecting PV systems from overvoltage, overcurrent, and ground faults. It is important to consult the latest edition of the NEC and to seek the guidance of a qualified electrician or electrical engineer to ensure compliance with all applicable codes and standards. Staying current with the NEC helps ensure the safety and reliability of electrical systems. Circuit breakers are vital components in electrical systems, providing protection against overloads and short circuits. Understanding their functionality and proper maintenance is crucial for electrical safety. Firstly, a circuit breaker is an electromechanical device designed to protect an electrical circuit from damage caused by excess current from an overload or short circuit. Its basic function is to interrupt current flow after a fault is detected. Unlike fuses, which operate once and then must be replaced, a circuit breaker can be reset, either manually or automatically, to resume normal operation. Secondly, circuit breakers come in various types, each designed for specific applications and current ratings. Miniature circuit breakers (MCBs) are commonly used in residential and light commercial applications. Molded case circuit breakers (MCCBs) are used for higher current and voltage applications in commercial and industrial settings. Air circuit breakers (ACBs) are used for high voltage and high current applications in power distribution systems. Thirdly, the operation of a circuit breaker involves several key components. A bimetallic strip or an electromagnet senses the current flowing through the circuit. When the current exceeds the rated value, the bimetallic strip bends due to heat, or the electromagnet becomes energized, triggering a tripping mechanism. The tripping mechanism opens the contacts of the circuit breaker, interrupting the current flow. Fourthly, circuit breakers are rated based on several parameters, including voltage, current, interrupting capacity, and trip characteristics. Voltage rating indicates the maximum voltage that the circuit breaker can safely handle. Current rating indicates the maximum continuous current that the circuit breaker can carry without tripping. Interrupting capacity, measured in amps, indicates the maximum fault current that the circuit breaker can safely interrupt. Trip characteristics describe the time-current relationship of the circuit breaker, indicating how quickly it will trip under different overload conditions. Fifthly, regular inspection and maintenance of circuit breakers are essential for ensuring their proper operation and reliability. Inspection should include checking for signs of damage, such as cracks, corrosion, or overheating. Connections should be tightened to prevent loose connections, which can cause arcing and overheating. Circuit breakers should be tested periodically to verify their tripping characteristics and interrupting capacity. Sixthly, testing circuit breakers typically involves using specialized equipment, such as primary injection testers and secondary injection testers. Primary injection testing involves injecting a high current directly into the circuit breaker and measuring the time it takes to trip. Secondary injection testing involves simulating fault conditions by injecting a signal into the circuit breaker's control circuitry. Seventhly, where a circuit breaker trips, it is important to identify the cause of the trip before resetting it. Common causes of circuit breaker trips include overloads, short circuits, and ground faults. Overloads occur when the current in a circuit exceeds the rated capacity of the circuit breaker, often due to too many devices being connected to the circuit. Short circuits occur when there is a low resistance path between two conductors, causing a high current to flow. Ground faults occur when there is an unintended connection between a conductor and ground. Eighthly, if a circuit breaker trips repeatedly, it may indicate a more serious problem with the electrical system. In such cases, it is important to consult a qualified electrician to diagnose and repair the problem. Ignoring repeated circuit breaker trips can lead to overheating, fire hazards, and equipment damage. Ninthly, circuit breakers play a critical role in electrical safety, protecting people and property from electrical hazards. Properly selected, installed, and maintained circuit breakers are essential for ensuring the reliable and safe operation of electrical systems. Tenthly, the use of arc fault circuit interrupters (AFCIs) has become increasingly common in residential and commercial buildings. AFCIs are designed to detect arc faults, which are dangerous electrical conditions that can cause fires. AFCIs can detect arc faults that conventional circuit breakers may not detect, providing an additional layer of protection against electrical fires. The NEC requires AFCIs in many circuits, including those serving bedrooms, living rooms, and dining rooms. Understanding circuit breaker functionality is crucial for maintaining electrical safety. Circuit breakers are essential components in electrical systems.